So, hello everyone, and welcome to week 11 of the weekly live discussions for the course Foundations of R Software. So, the main topic for week 10 was data frames, and week 11, the central topic is basically reading and writing data. So, reading from files, different types of files, text files, CSV files, and also writing to files. Now, additionally, there are also a few more topics that were introduced this week. So, some hint of descriptive statistics was provided, and also a discussion on the graphics capabilities of R. So, how to draw plots in R, that was also introduced. So, in today's discussion, we'll focus on data frames, reading and writing from files, and maybe a little bit of descriptive statistics based on what was discussed this week. But we'll leave the discussion on the graphics capabilities of R and the plotting capabilities of R for the next week, because most of week 12 content is concerned with graphics. So we'll discuss all the graphics together. I'll start sharing my screen, and as always, please let me know if you can see the R Studio window and if you can hear my voice clearly. Can you see the R Studio window? Okay. So let's quickly, revise what data frames were all about. So throughout the course, we have seen different data structures, which could be maybe as simple as just a scalar data type, or maybe slightly more involved, like a vector data type. The next level of abstraction was looking at matrices, which were two-dimensional vectors. Now, of course, you can always define arrays which are higher dimensional vectors. Then above matrices, we had lists, and finally, we have data frames. So when discussing matrices or lists, you are discussing about collecting different data types together, but the problem with matrices was that you can only have one kind of data within them. So if it's numerical, everything should be numerical. If one of the elements is set as string, that will, or character, that will cause an error. So if you want to treat it as character, the entire matrix has to be made up of characters. So this is where data frames are useful, because the kind of examples that we had discussed, for example, storing the records of students' marks. So usually records of those type don't just contain numbers, they contain additional information. So you can have the student's name, you can have the grade, which is also a character, not a number. So to store quantities like that, you need a more, involved object, a more complicated object, and data frame serves that purpose. So you don't have to create such an object yourself. This is one of the advantages of working in R. Again, there are so many built-in features which can be utilized based on our needs. The creation of data frames is straightforward. So let's say, let's pick out some entries that we want to fill in our data frame. So let's say 11 to 20, these numbers, and y equals maybe just these grades, A and B. Z could be maybe some names. Let's assume that X refers to the roll numbers of some students, Y refers to the grades, and Z refers to the name of their class teacher. So if I just want to build a data frame based on these, so I'm taking several assumptions here. I'll mention those assumptions in a moment, but let's just call this data frame student. So data.frame, and I will not specify any other arguments. I'll just mention the data using which I want to construct this data frame. So now you see immediately there is a problem. X contains 10 data items, Y contains 2 data items, and Z contains 4 data items. Now we know that usually when defining matrices or various other data structures, what R normally does is that if it falls short of filling in the entries, it starts from the beginning. But in case of data frames, there is one extra requirement that the number of objects or number of elements in the smaller collections, they should divide the number of object elements in the biggest collection completely. So if I had just changed Z, I'll just add one more entry here, and then call student, then this works fine, because both 5 and 2 divide 10. And now R will do what R always does, it will just start repeating. So X has 10 elements, you see those 10 elements in order. Y had only 2 elements, so 1, 2, 1, 2, it gets repeated. And Z now has 5 elements, so you see the 5 elements printed first and then they are repeated from the beginning. Now, of course, when you are building real world data frames, of course, the entries are not random, and these are just toy examples. So in those cases, of course, you have to be careful that each column or the entry of each column for a given row carries certain meaning. So you should be careful. I mean, what is being put in what order and what is being put next to what. Now I said that I will not look into any arguments here. So because of that, you see, the variable name automatically becomes the column name here. So if I want to access something, so the dollar notation allows me to access a particular column. And if I just say student X, it will give me all the entries of the column X. And similarly for student Y. Now notice the difference. This Y contains only 2 elements. That was my original variable. But student $Y refers to the entire column. So this will not just contain A, B, it will contain the entire repeated sequence. Now, of course, there's another thing that you can do. So while defining student itself, you can give some names to the columns. So I'll just say role equals X, grade equals Y, and teacher equals Z. So now if I call student, you see these columns have been named. And similarly, you can add row names and maybe so here, for an example, I've just selected the first 10 lowercase letters. It becomes A, B, C, D, E, F, and so on. But of course, if you're making a data frame which is referring to student data, then your row names are most likely going to be the names of the students. And you can add that here itself while defining the data frame. So row.names equals, and then use the collection and or maybe you have stored the student names earlier in a vector, so you just refer to that vector and this will be done. Alternatively, if I go back to the original way in which I had defined things, so no names provided here. There is one more way of defining row names, column names retroactively. So after you have defined this data frame, and then you suddenly realize that okay, you need to add this information as well. So now you have seen this symbol, this left arrow. This basically is similar to the equality sign, but this is something new. So you have the function name, which is appearing inside this inverted quotation mark. I'm not sure what the name of this thing is, but anyways. So now you give the name of the object for which you want to provide the row names, and then give something like 12 to 21. And similarly, so in this manner, even if you have already defined a data frame and you want to change the row names and change the column names, you can accomplish that. So now, okay, maybe I should store this. Okay, now it's statistics. Yeah, so just this right hand side is not enough. You have to update the original as well. So student equals and then the name of the function and then provide this updated value. So based on this alone, so let's say if you want to access a certain element, if you want to access the entire column that we have already seen, so you can just do student $x. And if you want to access a particular element, so from a row and from a column, just put L X. Yeah. Now we should remember these are stored as characters. So just giving L and X, it will look for some variables. So this is the first, the 1,1 entry, in other words. So just say student L, X, this is what will be returned. Of course, I'm not going to revise everything that was discussed last week because last week's discussion is available on YouTube. So we'll basically move on to this week's content. Let me just go back. Okay. I apologize, give me just a moment. I have to check something very quick. Okay, sorry about that. So I'll resume sharing my screen. Okay, so one of the first topics discussed this week was about importing data from files. Now, normally, you can have data stored in text files or CSV files, which is short for comma separated values. So, different files could have different kind of structure. So, this is just some random data files. So, it's not important what these mean, but it can be used as samples for our calculations. So, as you can see, here the data is separated by just a single space. If I expand, yeah, these are space separated values in a text file. You can have CSV values where there is comma separated values. So in any kind of data storage within files, some kind of separators are involved. Sometimes it's tabs, sometimes it's spaces, sometimes it's commas. The relation between tabs and spaces can vary. I mean, sometimes one tab equals 4 spaces, sometimes it equals 8 spaces. Depends on who's defining them. Now, you can see based on these two files. So you can ignore this first column. This is just a sequential ordering. So this is not the content of the file. Now, okay, so in this file, so there's a clear difference other than the separator. So of course, here the separator is space, here the separator is comma. But additionally, here you see the first column is a named column, or in other words, what we refer to as headers. Whereas in this case, that's not the case. So we have to be careful because sometimes if you, I mean by default, R assumes that there is a header present. If not, so it will automatically treat the first column as a first row as the header. So if that is not specified, then in a file like this, R will automatically treat these two entries as the column names. So these are some small things that we must be careful about when dealing with files. Now, of course, when working with files, the important thing to keep in mind is that the files are present in your directory or you have mentioned the full path of the file. For example, here I can see from the files pane that all these files are inside this R course folder. I just need to make sure which folder I'm in. So I'm inside the R course folder and the content of the R course folder is shown here. Now, I'll only discuss two types of examples, CSV files and TXT files. But as it has been shown in the lectures, file reading can be done for a variety of file formats. So even for HTML format or even the Excel format. So XLSX format, which is used by Microsoft Excel for spreadsheets. And of course, for other type of softwares like Minilab and so on. So let's start by reading the CSV file. And the command is pretty simple. Just mention the file name. So let's say we read the first one. It's t115_h.csv. And of course, we don't just want to read this, we want to store it in some variable. So since I'm reading from, we have to distinguish between these two. So one refers to some h, one refers to some phi. So I'll call this data h. And just enter. So now you see automatically everything that was in this file gets stored in this variable. There are 10,000 observations and contains two variables. So if I try to print data_h, so it has printed first 500 entries and then the others have been omitted. But you see, now of course, a slight difference between how the header was stored in the original file and how it is stored here. But that's fine. It does not affect the data that we are trying to work with. Or maybe for simplicity, I can just change the header. I'll just call it H. Save this, and this one we'll just call file. So let's clean the screen and redefine this. Okay, so that's R and H. Now we can check what kind of structure is this stored in. And this is a list-like structure, and we can also check, is it a data frame? And that's true. So basically you can access these elements. So if I call data.h $r, and this basically gives an estimate of some of the contents there, and similarly data h.h or $h. So maybe I want to look at the second hundredth, or just say from, I want to look at a slice of 100 data pieces from this. Now I can do all sorts of mathematics on this. So maybe we try and see what's the mean in this sector. Now let's change this. So we are in this segment, and the mean is different. We can go higher. See, so of course there is some pattern inside these data, and that can be studied. Now you can also name these headers. Okay. You can name these headers differently if you want. So you just set names in data h. So there's two of them. So I'll just say first one is radius, and second one called field value. And see, the names have changed. You can also ask for the summary, since this is a data frame. Now, of course, because radius was equally spaced, it started from 0, goes all the way up to 10,000. Field value starts from this large value, or reasonably large value, 1.54 or 1.55 approximately, and the smallest value that it assumes is this. So of course, if you take the mean of the entire thing, because most of the larger values are accumulated at the beginning, and very soon the values drop out. So the mean is nearer to the smaller value, or it's nearer to 0 rather than this number. Now, so instead of this CSV file, if you are trying to read the txt file, and we want to store this in a table, so we'll use the command read.table, and let's store this. Let's borrow the name from the file itself. Let's call this JB. Now I'll just mention the file name. I'll look at the other arguments later. So let's just call this JB table.txt. And now if I call JB, so let's compare if it has picked up the right values or not. So this is working fine. I think there is one more command. Okay, read.data seems to not make that mistake of read.table does not make the mistake of picking this first row as the header automatically. So I think that's a problem with the CSV method. So let's say if we just remove this. And let's clean the screen. Let's go back to accessing data H. Yeah, so it's actually read.csv which makes that mistake. It's not about reading from CSV file or txt file. So if you don't want to automatically assume a header, and you basically
we have to give the command head false, right?
yeah, that is. Okay, but one difference you can note on the right hand side itself. So the last time we did that, it read only 9,999 observations, but this time it's correctly reading 10,000 observations, and it's not automatically, interpreting the first row as the header. They're just small things that we must be careful about. Read.table is a little more intelligent than this. So it's called JB. And so if we check, is JB a data frame? It'll come out to be true. And JB.coolNames. So by default, these are the names that R automatically picks up: v1, v2, so vector 1, vector 2, and so on. But of course, you can change that. Names of JB, you just change them to, let's say, this X, and the other is JB of X. So this looks more like a mathematical table. So for transparency, I can just mention that these JB, JF are some thermal functions. They appear in thermodynamics, but these involve an integration over the logarithm of the exponential of something, some complicated function, and these cannot be evaluated analytically. So we need tables like these to I mean, so whenever these appear in our calculations, we need tables like these, and we read values for different choices of x, and then corresponding to that x, what is my jb of x or jf of x, that we then substitute in the calculation. Okay, so one thing about txt files. So if you are using this read.table command, so by default it is assuming that the data is separated using spaces. But if that is not the case, so let's say you're trying to read a CSV file, but you're using the read.table command, then you must explicitly mention that the separator is a comma. So let's go to this. If you do it like this, what happens is it treats the entire thing as one, so even including a comma, because it was looking for, by default it's looking for a space as the separator, and there is no space, as you can see from the CSV file. So there is no space, so don't think of this as the space, this is just artificial. So these are the contents of my file. So that's why if you are reading a file like this, it may happen that, so in some softwares, so for example in Mathematica, you can, just like in R, you can read and write two files, you can do that in other software as well. So it may happen that you have set the extension of the file as .txt, but you are storing them as, the entries are stored as comma separated. So in such a case, you should mention the separator is a comma. So now you see it automatically got updated. It was treating 10,001 observations of two variables. Now it will treat this as 10,001 observations of two separate variables. So it has made the separation. But now there's one more thing to keep in mind. So header equals true is the default setting in read.csv, but header equals false is the default setting in read.table. So it's automatically reading the header as well. So in this case, again, these are small things, but create a lot of difference and can cause a lot of annoyance if you're not careful about them. So I have to set header equals true, because I know that in this file header is there. Now the number of observations is correct. So now if I call y115, so now instead of v1 v2 we have r and phi at the top, as it should be. So of course there is no hard and fast rule that you should always read .txt files with read.table and .csv files with read.csv. You can interchange, you can mix, but please be careful what are the default settings for those commands and what kind of differences may appear. Okay, so that's all on reading from file. Now of course, just like you can read from file, you can also save your data to a file. So let's say we just work with some, so we already have x and z. So we can try and write these to some files. So the simplest command for that, let's say write what you want to write. So I want to write x. Where do I want to write it? So I'll create a new file, or just call it x file dot txt maybe. So it's not necessary to give an extension, because you're doing this console based work. It will just convert whatever the content of that file is into bytecode and then read from that. So whether it is .txt, .csv, those are useful when you're working with more specialized software. So something like Microsoft Excel will treat a TXT file or a CSV file in a different way than will treat a XLSX file. So those are high level software specific. So for example, if you're working with Linux, you may have come across the open document text format or the open document spreadsheet. So .ods, .odt, and so on, or .odb for the databases. But if you're using Microsoft, you have .ppt, .docx, .xlsx. So these are, I mean, software specific, but restricting to command line tools, it doesn't make much of a difference. What changes is that .txt and .csv are very simple formats. So there's not a lot of formatting involved. But a spreadsheet is more complicated because there's a lot of metadata involved. So that's why file sizes also become larger. So as long as you are working with, I mean, small projects, these simpler file extensions are sufficient. But of course, for more specialized cases, you may need to have specific file extensions so that specific behavior can be invoked. Anyways, so okay, will not specify n columns here. We'll just have 10 entries. So just assume that this will go one after the other. Now, as you can see, separators are, again, if you want to break things in two columns, how do you want to separate them? And similarly, append, basically. So append is important because the way default file operations work is that either you add to a file or you overwrite a file. Or the third option is you create a new file. So if you're specifying a file name and that file already exists, then if you say append equals to true, then whatever this new data that you are writing will get added to the original data. I mean, it will appear below that. But if you said append equals false and that file name already exists, what will end up happening is that everything will get overwritten. So if you don't want to do that, maybe specify a new file name, or maybe don't store files of the same name in the same location. And if that file does not exist at all, then a new instance will be created. So we'll just simply do this. Now if we come back to files, you see an X file is created here. So we can open this and see what's there. So the default setting for this was, again, if we hover over the right command, for n columns, the default setting is that if X is a character, then just one column, otherwise 5. But we can change that. We can just say X is not a character, but I still want to use a single column. So now you see everything is in a single column. Of course, I can play around with this. I can say 2 columns, and I have not mentioned any separator. Now you see what is happening. So, okay, this time let's change the append behavior as well. So append equals true. So now you see this was not overwritten. So the old content stayed there, and the new content was added after this. So let's change this a little bit more. I'll call it, let's make it 5 columns, and this time we want the separation to be comma. Of course, you can be a bit more creative, and now let's remove append equals true. So this is basic file writing. Now, of course, as you can see, separating them by spaces or separating them by commas, I mean, you can and also by changing the file extension, you can make the file behave like a CSV file or a TXT file and so on. But of course, you can be more specific and you can just say write to a CSV file or write to a TXT file. Sorry, write to a table. Just like you had read.csv, you have write.csv. Just like you had read.table, you have write.table. And they offer more, functionality. But the basic write function is also sufficient for small tasks. Now let's say we want to do something more complicated. Let's try to write the student object is there. Let's see what happens with different options. So what I want to write is the student object. The file I want to use, I'll just call it student info.txt. We want 4 columns, and the separator will just leave it as space. Okay, so I think we'll just use Okay, so if you remember our discussion on reading input from the console, then we had highlighted this point, very clearly, that whenever we read from the console, the data is automatically treated as string. So everything else here, so other than those which are actually numbers, you see, A and B could have corresponded to some variables, but now that they are part of a file, they're all strings. So there's a slight distinction between reading and writing. So reading from a console and reading from a file. So from a file, you can have specialized arguments that treat numbers like numbers. So that's why we know that the contents of the CSV file, these are numbers. And when we did read.csv, these were stored as numbers. Similarly, we know from this student info that only the first column is a numerical column. Everything else was characters or strings. So that's why when it's written to a file, the data type is handled appropriately. But of course, when you print to the console and read from the console, everything is treated as string. So that's one advantage of reading from files as compared to reading from the console. Now, of course, there is a practical advantage as well, because as you saw in these files, there are 10,000, 20,000 entries. You can't enter 10,000 data entries from the console. That will take a lot of time, and that's not very productive. So, of course, you can explore more on reading and writing. There is a lot of documentation available that can be utilized. But we'll wrap that discussion up here. And now there was some discussion on descriptive statistics, a very basic surface level discussion. So maybe we'll look at that. So there's, of course, two ways in which statistics can be helpful to us. So one is descriptive, the other is inferential. So descriptive statistics is more about you have some data and you just want to describe the data. So what can you say about the data? Maybe you can put the data in some order, some increasing, decreasing order. You can, based on that, you can study how the data varies. Data is something as simple as you draw a graph of y equals sine theta, and you can maybe comment looking at the graph how y is changing as theta is changing. Y equals sine theta is a very simple example. So maybe you have something more complicated like x square minus y square times cos x, something like that. So now you can study how the features are changing as x is changing or as y is changing. Now, if you feed in numerical values, then based on that, you can also see what are the central tendencies. So there are three types of central tendencies that are very commonly spoken of. So mean, median, and mode. Mean is sort of the average value. You add everything and then divide by the total number. The median is if you put everything in order, what is the middlemost element, and mode is what occurs most number of times. And of course, you can also study some relationships within that data. What is greater than what is smaller than what, and so many things. For the simplest case, let's say we have this collection. So let's call it data 1. And we have this collection. So 1, 2, 1, 2, 4, 1, 3, 1, 1, 1, 4, 2, 3, something like this. Now, of course, this is just a vector, but again, numbers are the language in which we are communicating, but these numbers could have more meaning if we are looking at real world examples. So this could maybe be the list of the number of days. So let's say there is a bunch of students. Again, let's come back to the examples of students. And each of these entries, they basically denote how many days they have been absent from class. So there are some students who have been absent from class for 1 day. There is a larger number of students that have been absent for 2 days. And some have been absent for 3 or even 4 days. So one built-in function, which is our friend, is called table. Now, of course, if you want to study the frequency based on how many times 1 occurs, how many times 2 occurs, or 3 occurs, or 4 occurs in this data 1, the most naive way is by looking at it and counting it. But again, we can automate that. We can automate that by using this table command. So what it does is that in tabular form, it gives you each entry and its frequency. So we can say that 7 students were absent for 1 day, 3 students were absent for 2 days, and 2 students each were absent for either 3 or 4 days. Now, this is very helpful if we have large data. So let's see some large data that we have. So let's see if we can apply this on some of the data frames that we have constructed. So this will end up taking a lot of time. Okay, we should maybe use a smaller sample. So let's use something like I have data H. Let's take V2 and only a small sample of this. So say from 1000 to 2000. Now see, corresponding to each entry, the frequency is 1, because what that data was describing was a simple curve. So a discretized curve, so to say. So it's not entirely continuous, but we have very closely spaced points. And of course, there are no loops in that curve. So each point on the curve, or corresponding to some x value, that y value only occurs once. So that's why everything is returned at 1, 1, 1, 1, 1, and so on. So, but of course, it's possible that if you work with periodic data, so let's say x is these numbers, and let's say y equals sine of x. It's possible, let's say, is y periodic or not. It's not easy to see the periodicity. If we do table on y, yeah, it's hard to see the periodicity in these examples, but anyways, so that's the purpose of this table command. Now, what you have here are the absolute frequencies, how many times something actually appears. But sometimes the question can be about the relative frequency. So the proportions in which you can divide the entire set. So you just do table on data divided by the length of data 1. So you can see in total, so 7 and 3, 10 and 4, we had 14 data points. Half of them are 1, and then the other entries appear in different proportions. So there's 14.28% threes, same percentage for fours, and 21.42% or 43% twos. Now, of course, there is a separate course running on descriptive statistics, or I think that course has wrapped up by now. So we do not dive into much detail about descriptive statistics in this course, but of course you can use some of the commands or some of the most well-known ones. So for example, you can ask for quartiles. Quantile, quartile. So quantile is basically tries to, you give it some interval, so data which spans some interval. So let's say data from 0 to 100. It will try to split that data into 4 parts, or fourths, 1/4, 2/4, 3/4, and 4/4. The output of this quantile command, what it does, it gives you the boundary values. So 0% corresponds to the smallest value in that interval, and 100% corresponds to the largest value. So it's basically, if you arrange this in order, then 25% of data falls within this number and this number. Next 25% falls in this number and this number. Similarly, the next 25 is here and the last 25 falls here. Now, just like quantile, you also have do we have a built-in command or not? Okay, decile doesn't have these commands are not there. Anyways, so just like quantile, statistically you can also define deciles and percentiles. So what decile does is splits the whole thing into 10 equal pieces, and percentile will do the same thing but into 100 equal pieces. So based on that, you can know more about your data. So how the data is arranged and what sorts of intervals are involved in the data and so on. Okay, like I mentioned in the beginning, there was also an introduction to the plotting capabilities of R, but it will be more appropriate to discuss that next week because week 12's lectures are mostly concerned with plotting. So we'll discuss all the different kinds of plots that you can make in one lecture or in one discussion session. So now, are there any questions from your side? If not, then say goodbye and we'll meet
So
again next week.
I just have one question, sir.
Yeah, sure.
Is it safe to have my own data in R?
Yeah. Because it's being stored locally, right?
Okay,
So we're not connected to any server or any other external tools.
okay.
So it's safe, reasonably safe.
Thank you.